All right. So welcome to the second last day and probably the last lecture of this NSM course on OpenACC. So we have been looking at different aspects related to OpenACC constructs, and since last 2 days we have looked at specific ways in which you can use these constructs in certain small pieces of code. Vectors and matrices is what we were looking at. Today, the agenda was to look at a specific application which makes use of possibly these vector and matrix operations. And I had listed substitution cipher as one application, but it turns out that it's a really simple application. So we might finish it rather quickly, and then I'll explain a couple of more applications which might be helpful from the perspective of overall parallelization of the application that you might encounter in your, let's say, in your world. Okay, so that, and then we'll kind of summarize this particular course. Okay, so let's come to this specific application of substitution cipher. So the idea is that we are given a string, which is also called as plain text. We would like to encrypt it using a function which maps each character to a different character. Right? So for example, I might say that OpenACC might get O might get mapped to P might get mapped to Q, and so on. Right? So this is the next character that I am suggesting in this particular substitution cipher. Is this really a good cipher? No, this is definitely not a good cipher and not the one that really gets used in practice. But for the sake of understanding the basics of cryptography, this is typically taught in the earlier days of cryptology or cryptography course. So our job is to implement that. So can people write simple C code or Fortran code corresponding to this transformation? So you can just assume that there is a string given to you and just write it such that you get the next character. Okay, so I'm assuming that you'll be able to write such a code now. The advantage of such a mapping from the perspective of this course is that we can perform this transformation, character by character transformation in parallel, because one is not really dependent on the other. O always maps to P and P always maps to Q. So there is no dependence across parallelizing O first, or executing O's transformation first and then P's transformation and so on. So this is a good data parallel operation, and because of that it also scales very well when the input size increases. That is, larger the input string and you have enough number of cores or even enough number of threads to execute this in parallel, it's going to give you higher and higher speedups. Right? So that is what we call as nicely data parallel. Sometimes this is also called as embarrassingly parallel operation. All right. So right. So the source corresponding to it is in cipher.c in the list of all codes. We'll take a look at that, but before that I would like to, just the usual sequence of steps that we follow towards getting this in parallel. Right? So we'll look at that in a while. And one homework exercise before we look at the code is to implement this substitution cipher such that it's not fixed, in the sense that characters don't map to only, let's say, character I doesn't map to I plus 1. Maybe it maps to something totally a random alphabet. Right? So how will you implement that? That you have to think about. Or not even I plus k or I minus k. It should be totally arbitrary. Right? So please think about how you will implement that. Okay, so let's look at that code, which some of you might have thought of writing also. So we have this plain text as a character array, encrypted text, and then the decrypted text. We expect that this decrypted text matches the plain text if your algorithm is implemented correctly. Let's say I initialize it with this particular string, and then when I try to encrypt it from plain text to encrypted text, and then I try to decrypt it from encrypt text to decrypt text, right? So this is just to make sure that I do it correctly, and then I print those strings onto the screen. How are these encrypt and decrypt functions implemented? Well, these are implemented as a transformation onto the plain text, where I specify by how many characters you want to change, by how many ASCII values you want to update the character. So the plain text to encryption goes in one character next, whereas encryption to decryption happens, let's say, 25 characters next, so that when you do it in a mod 26 manner, then you get exactly the same letter back. Right? So that gets implemented in a certain way. For example, you can go over the source string, you have the destination string and the distance given for mapping the characters. So you have a pointer which goes over the source string, another pointer which goes over the destination string, and while the p pointer, that is the plain text pointer, is non-zero, you go on adding and then you go on incrementing both the pointers. What you do with each character is essentially find out what is the number of this character from 0 to 25. Right? So that we will do by the character minus a gives you that distance. Gives you the number in the ASCII values from 0 to 25, plus distance gives you the next number, and mod 26 is going to take care of this wraparound. From z it should become a, and so on. And that you add to the ASCII value of a, and you get the modified character which you assign to EPTR. And the way this gets implemented because of this distance parameter is you can use both encrypt and decrypt in the same manner, that is, they are using the same transform function. So this turns out to be a relatively simple program which you can implement. But any questions on this code? Okay, so assuming that this code works, and it does work at least on these strings that I have tested, how do you go about understanding how this particular code is transforming the string? So it turns out that as far as NSM is concerned, it will get transformed to the next characters. So N will become O, S will become T, M will become N, and so on. But space also gets transformed. Right? So while that is probably okay from your perspective, maybe when you are sending this information, you don't want that space to get converted. So you might want that the special characters other than the usual alphabet characters A to Z, small and capital case, I don't want to transform them. Right? So therefore you add a small condition there that if it is between A and Z, small a and small z, then only do this transformation, otherwise don't do. Because of that, the capital NSM will not get transformed. They will appear as it is, but the small case one will get transformed, and so on. So that is probably an application dependent, some semantic information which you can get. But because of this, what happens is you have this for loop which was earlier nicely parallel. Now there are conditions which got added to this, which is going to get executed by each thread repeatedly, and especially in the context of GPUs as accelerators, we should be aware that too many conditions inside the kernel may not be good from the perspective of GPU execution. So there is something called as thread divergence, which might occur because of conditions inside the code, which we would like to avoid. So if it is nicely data parallel and you don't have any conditions and so on, every thread is doing just some transformation operation, then that is better. When these conditions come, then it is not clear. Some threads might be doing the if part, some threads might be doing else part, and that is not good from the SIMD style of execution or single instruction multiple data style of execution, which is quite common in the context of GPUs. Right? So this reduces some performance, so you should be aware of this. But then if the application semantics need it, we can't do much about it. But there may be other ways in which you might want to transform. For example, maybe there is a way I can make this if condition outside, where maybe the string goes through some sort of a pre-processing, where I convert all the small case letters to something else or non-small case letters to something else, and then when it by the time it comes here, you can just increment all of these without having any condition and so on. So that those pre-processing steps might be helpful in some contexts, but yeah. So then once we have this code, how do you? Oh, by the way, did I not add /0 in the previous code? I think /0 was not added, right? So here, while this is non-zero, so I think I'm not adding the /0 for the encrypted text, right? Which should get added, right, at the end of this for loop, which seems to be present here. This /0 is important because I'm making use of that as a string. Yeah, that /0 is important. I think that is missing here. That should be added. Okay, sounds good. So this is the correct code. So how do we parallelize this? Well, the best way is that, okay, look for the for loop, and then I'm going to add pragma-acc parallel loop there, and that is going to make this code parallel, and that is going to be our start, right? And then from there, what all the other transformations that you can do? For example, the data transfer, how does that happen, and so on. And as soon as you add the data transfer, I mean, so what is happening in this case is that I'm just going to go back further. So as far as this transform is concerned, that is taking the source and writing to the destination. So it is reading SRC and writing DST. Once DST is written, it is going to be, so in this case, plain text is the read only part, encrypt text is the write only part. This write only part is going to be fed to the decrypt function. And that means that you might want to, and assuming that this decrypt is on the GPU, running on the GPU, you might want to keep the encrypted text directly there. If not, then we have to copy it out, right? So that is what this code does, where it's trying to copy out the destination, right? But if you do it only here, then you might end up copying it out at the end of encrypt and copying it in again for the start of decrypt. Of course, you will not use encrypt and decrypt together, but assuming that this is your application, you might want to reduce that unnecessary communication. You want that data to be available on the GPU across the calls also. And that is where which construct comes into picture? Which construct helps us in making sure that the data is there on the GPU memory? Okay, so it's the data clause that helps us, and hopefully that will help us in reducing the overall communication. So at this stage, I'll unshare the screen and share the full screen so that I'll be able to show you the code directly. Okay, so share the entire screen. And from this, we can look at the cipher. Okay, so I hope this code is visible. Yeah, can somebody confirm that this code is visible?
Yes, visible.
Okay, great. Okay, so sounds good. So we have this code, which is what was there on the screen, just that we are using a different string here, but this star EPTR is missing, right? So there should be this star EPTR equal to slash 0 or 0. So that should be there. Okay, so let's parallelize this and let me directly go to cipher 2 pair 3, right? So that is our final code. The intermediate ones add different pragmas there, but if I don't add the data clause, then that is going to be using this copy out of DST. Uh, in this specific case, right? So far we have been using these arrays and matrices, but if it so happens that you are not able to specify the length here, then you might, and the compiler may not be able to figure out, then you might want to specify it explicitly here. And that is why I'm also making sure that I'm passing this srclen as a parameter, so that which is essentially the string length of that particular text, right? So that is what is getting passed. So string length doesn't cover /0, so I need to add +1 there, right? So that is one way. Okay. So now what we have to do is to add the data clause there, and you have to help me in this exercise. So this copy out is probably not going to be required here once I add the data clause. So let's add that. Okay, so what do I do? Hash pragma acc data, and what should I add to make sure that I don't unnecessarily copy things here and there? Any suggestions? Or maybe there is something in the chat. Okay. Pranav had said that the screen is visible. So any suggestions on what we can add further? Right. So we'll do more like a interactive way. We can reduce the size of this so that I can see the chat. Okay, I'm not getting any answers, but essentially we want that the plain text should get created and also copied, because this plain text is received from the user, right, in this case, and therefore it is already populated. So I would like to copy in plain text, right, and I can as well specify the length, whatever, 0 to something something 0:n or something like that, but that won't be necessary here. You can optimize it because not all the n locations might be used, so you can add string length there. That is also okay. And once you have the plain text written and then the encrypted text, that encrypted text as well as the decrypted text are going to be used outside this data block. That means that I need to get those back from the GPU. So I'm going to write encrypt text and decrypt text. Okay, so this seems to be all right, that I am able to copy in only the plain text, and I'm going to get both encrypted text and the decrypted text outside the data block. So that part seems to be okay. But because of that, there is some change which I should make. Where is that change?
So you should initialize the plain text, maybe.
Initialize the plain text where?
So, we should give a value for the plain text array.
Okay, so I'm assuming that that will get populated here because of the getS function. Is that reasonable, Pranshu?
Yes, sir. Yeah.
Yeah, and then you will copy it in to the GPU memory. And then this can run on the GPU and so on. Okay, so that sounds fine. So one change that is required is this. Here we don't need to really copy it out at the end of the function. This is just run it in parallel on the GPU because the data is already available. Both the source and the destination are going to be available on the GPU. So one additional thing which we can do here is to create these. Right? So create again the same two character arrays on the GPU and then copy those out at the end of the block. Right? So that is going to be helpful to us. Okay, so that part seems to be all right. Any other changes we would like to do to the code? For example, can we use collapse here? Can we use styling here?
Sorry, can you explain like why we are using this create, encrypt, and decrypt again?
Yeah, so create because we want this encrypt text and decrypt text to be the arrays available on the GPU because those are going to be used on the GPU. So as far as plain text is concerned, that is anyway copied. But encrypted, decryptors need to be created. A copy of those need to be created on the GPU memory. Currently, that is created here on the CPU. So even if you don't specify, it is going to get done. But I mean, we can be a little more explicit here by specifying that create should be done. Right? And we don't need to copy in because encrypted text and decrypted text are not containing anything useful currently. So we just create the way we have done, right, for our matrices ABC, where we were doing C equal to A plus B. We said that copy in AB and then create C. In a similar manner, here we are doing copy in plain text and create encrypt text and decrypt text. Okay. Any other concerns, questions? Okay, so we can't use collapse here, we can't use style here because that requires two loops to be converted as a two-dimensional parallel space should be there. It's a single dimensional, so that's not a concern. One thing that you can do is you can play around with number of vectors, number of gangs, something, or let's say vector length. So you can play around with these values, and maybe it will change the performance. I mean, definitely it will change the performance, but maybe it will not change it too much, right? As the problem size grows, for example, I'm talking about maybe n is much larger. The getters may not be a good function for them. Maybe you can initialize it with arbitrary characters and then check if the performance is going to be what you expect it to be. Okay, so this is what we are able to do with respect to this ciphers, this encryption and decryption program. All right, so we'll move ahead from here. I'll close this. Let me go back to the slides. Okay. So the next method that I'm going to talk about is a numerical method, and we are going to go from one-dimensional to two-dimensional now. Our character string was single dimensional. Now we are going to talk about a matrix. So LU is a method where you might be able to convert a given matrix A, let's say square matrix, into two matrices. One is the lower triangular matrix, another is the upper triangular matrix. That is why this method name L followed by U, lower triangular and upper triangular, such that A equal to L dot U, such that the original matrix A can be obtained by a multiplication of L followed by U. This is useful in multiple applications, including solving system of linear equations and so on. Because essentially, if you have the lower triangular matrix, you can take, that means that you have single variable in the first row, then two variables in the second row, including the first one and so on. So you can do substitution and solve it. So it's useful in multiple domains. Our interest in this case is to, can you have this algorithm implemented in parallel using OpenACC constraints. So how does this method look like? Well, it's given in that lu.c, which we will look at. But if you look at the formulae associated with this L and U, you'll be able to figure out pretty quickly where the parallelization lies. Right? So many times in your simulations or research work or other professional applications, you'll be given these functions, and you are asked to write a code corresponding to this. So an element of this matrix U, which is ij, is obtained as aij minus summation of k equal to 0 to I minus 1 of L of ik and U of kj. Right? So this ij is dependent on the previous values of U itself and also the lower triangular matrix. So these are so that means that U is dependent on the L, and then if you look at the L value, that is also dependent on A, which is anyway static fixed, but it is also dependent on both L and U, the previous values of L and U. So there is a circular dependency in this aspect from U to L and from L to U, and therefore this needs to be repeatedly solved, typically until a fixed point, until you reach a particular stage where you have the factorization of this matrix done. All right, so let me open up that lu.c. Okay, let's go to main first. So what does the main do? It has this original matrix A. It initializes that matrix and then performs LU on it. Why do we need to initialize? Because I want to check if that LU is performing correctly or not, and then I print this matrix A. In some applications, you might want this L and U to be separately maintained, but then in many other applications, what you do is you don't maintain a separate L and U matrices, but you maintain it as part of A itself. And therefore, there is an in situ update happening to A, where the lower triangular part refers to L at the end, and the upper triangular part refers to U. What does initmat do? Well, initmat is just performing a loop to initialize a vector. Why do we have such a primitive? Because then the init vector primitive can be used for initializing a vector itself. So we are initializing mat of I row, right, with some values as parameters which get used in the function. Right? So don't worry about what that initialization is. That's not very important. Typically, you will have some application-based initialization which you will read from a file. So essentially, there are two loops here, one for the I and then another for the J. And therefore, you will be able to use collapse here. But whether that collapse will work across these function calls, that is not clear. Depending upon the compiler, it might not work out. And therefore, you might have to be content with single level parallelism in this case. Right? Okay, so that is one part. The second part is the actual LU. The actual LU happens as again nested loops, but there are two parts to the nested loop. The outer loop starts with I, which is going over all the rows. The inner loop has two parts. The first one is going from, depending upon, I'll just go back to the slide. So here, since U of ij needs to go from k equal to 0 to I minus 1, so therefore the inner loop is going to be dependent on the previous loop, right? So here, although I'm talking about I, essentially that is going to go from, so I and j are okay, that is going over all the elements, but this k loop needs to go from 0 to the previous index, that is jj minus 1, right? So that is our u part, and that gets initialized here. Right? So this update is happening aik into akj, so that is lik into ukj, right? So that is what is the, since we are using A itself, that becomes the variable. Instead of L and U, I'm using A itself. And then finally, we have to do a division using this A of JJ, that is this. However, when we are doing this division, yeah, so this seems to be the L part rather than the U part, because there is division happening. So since this division is happening, that is this part, and that also has IK followed by KJ, so that is okay. The U part is here in the second loop. Yeah, but more importantly, what I wanted to convey is that this division is happening, but this division can sometimes lead to unpredictable results. The reason being that A of JJ, comma JJ might turn out to be 0 or very close to 0. I mean, in this case, I'm taking integers, but in general, you can have, okay, actually, I'm taking float here, right? So the floating point value can be very small, in which case you might see some not a number values being given to AIJ. To avoid that condition, you can add a small check. This is what the numerical methods usually do, that if the value is very small, then you don't compute anything, you don't perform this division, but otherwise you perform this division. So again, that application specific aspect we are not interested in. We are interested in looking at, given this sequential code, how do you parallelize it, where all we can add the parallelization. And I would like you to think about how you will add parallelization in this case. So let me just check if there are any. Okay, there are no questions. Yes, I leave it here for some seconds, and then we'll look at the final parallelized code. Okay, so from the perspective of parallelization, we are essentially going to add pragmas here, right? But there is one important thing from the perspective of pragma, and then we can add the data clause, etc. here. So that is kind of standard now with whatever we have been seeing. But there is one important point which comes in this application, and that is this for I loop has this for j loop for computation of L, and the second for j loop for the computation of U. This way of, and these two loops are sequential. That means there are two steps inside the for I loop, and therefore this is not in the standard format, and therefore you won't be able to use a collapse clause for the case here. So when you add the pragma here, hash pragma ACC parallel loop, I won't be able to use collapse to here because it is not in the standard or normalized form. Right? So there are two for loops here. Right? So that kind of forbids some parallelization. But is there any way I can get away with it? How can I implement a collapse here? So that is the question. At least collapse 2, if not collapse 3. Rajan says after II. Okay, so that's a good point. So let me, instead of here, maybe I'll add here, and then will I be able to say collapse 2? Any suggestions if this is correct or not? Rajan, what do you think? Okay, so this will also not work. The reason being that if I apply this collapse to here, then for j and for k should be in standard format. Right? So as far as k loop is concerned, it is in standard format. That part is okay. But the j loop contains this for loop and then this assignment state. And therefore, we won't be able to use collapse to here. Right? So there again, we are in trouble. But what Rajendra said is possible if you move this here. In this case, since that final division is not present, the two for loops J and K are in standard format, and therefore you will be able to apply collapse to that. So that seems to be good. Is there a way I can apply collapse to still for the earlier loop or loop nest? Any suggestions? Okay, so one of the ways in which that gets done is a code transformation um called as loops splitting. So I'm going to convert this into two loops. So Rajana said, why the division creates a problem? The division becomes another statement inside the J loop. So there is for k and then division as two different statements inside the for j loop, and therefore that is not in the standard format. Okay, so if I can convert it into these two parts, now these two are separate loops, right? So there is a for I, then j, and then k, and within that k is standardized, j is not standardized, and I is standardized. Now, as far as this second loop is concerned, again it goes over the same I because I have taken it out, and then it goes over j, k, and then it is completely in standard format. And in this case, I may not be able to apply. Yeah, so I'll be able to apply this collapse to here because for I, this is a single loop, right? So I'll be able to combine this I and j. And as far as this second loop is concerned, not only collapse 2, I might actually be able to use collapse 3, assuming that that is going to give you some benefits. So that is the advantage which you can get by doing this manual transformation of the code in the context of not only LU, but there will be other methods, other numerical simulations which we encounter. So this also is something which we have to keep in mind. Right? So this is not really related to OpenACC, but since this collapse is specific to OpenACC or even tiling, right? So you can change it to tile 2 or something like that. Not tile 2, we'll have to specify the indices tile II and JJ. Unfortunately, this will not directly work. What you will have to do is to take out int II and JJ outside. So this is what will be required for making that tile to work, because by the time you read the tile, I and JJ are not defined at all. Okay, so this is what I was saying, that once you transform these loops, then you will be able to probably parallelize those better. Right? Apart from the usual data clause optimizations that we can have, as well as other parallel addition we can do in the init clause, init function. All right, so this sounds fine. Any other things that come up here?
Hello.
Yeah, otherwise it's okay.
I have a question.
Go ahead.
I have a small doubt. Like this.
Yeah, sorry, I'm not able to hear. Sorry, I missed some of your earlier part of the question. Can you repeat that, please?
Will this collapse 3 won't cause? I mean, will this collapse 3 cause correctness issue, like at line 45? because
Line 45. I mean, the correctness issue because of this. So, Josh, you're asking.
yeah, yeah, I'm asking
Okay,
about
so I
that
couldn't
same
hear
line.
the question. Right, right. So that's a correct observation that when you do a collapse 3, will it cause some issues because these indices are not now no longer, I mean, these are not completely parallel indices, right? So there is a data dependence across these. So for multiple values of k, you are actually writing to the same ij pair, right? This is similar to what we have in the context of matrix multiplication. So it's possible that you whether so the question is whether you get a wrong answer because you are doing things in parallel. In this case, it so happens that you won't get a wrong answer by parallelizing this k loop. The compiler is able to figure out that this is plus equal to, and then it will generate a reduction or atomic corresponding to this k loop. But you will lose on performance because if you had run it actually sequentially, you would have probably it would have been better than adding that additional synchronization for taking care of writing to a of ij as well as reading from a of ij. So yes, it doesn't cause correctness issues, but it can cause performance issues. So you might actually be better off in this particular example to keep it collapse 2 rather than 3. That is correct observation.
But there is one more
All right. Any other
issue.
concerns, questions?
Sorry,
Yeah,
I
go
have
ahead.
one more issue.
Hmm. So your voice is breaking.
No,
Just.
oh, sorry.
I mean, I'm not able to hear the complete question. Sometimes the part of it comes out.
Okay, probably we'll discuss it offline then. There is some
Or
other issue I feel that.
okay, maybe you can type it, or maybe you just say it. Maybe if the connection is okay, then I'll be able to hear it completely. Go ahead.
Matrix, right?
Hmm. Okay, I'm sorry, but there has been a break in voice. I don't know if about others, whether they are able to hear just completely. Yeah, maybe Josh, I suggest that, okay, Rajanya also is not able to hear him properly. So maybe just you can either type the question or we can discuss it later. Sorry about this. Okay, so we'll move ahead from here. So this was our LU part, and then you can add the usual data clauses here. ACC data and so on, right? So there will be some processing that we can do here, some optimization with respect to the data transfer and so on. Okay, so this part is also all right, but let me show you the final code. Right. So this was our usual pragma where we created the A and we also copied out A because we wanted to do print matrix A in the end. Thankfully, there is a single matrix, so that is not really an issue. As far as this LU is concerned, currently you can do parallel loop. So in this case, what I have done is not parallelize the outer one, but only the inner one. Um, and we have to apply this present clause to make sure that the compiler doesn't generate code. Yet another way is to you can play around with num gangs, num workers, num vector length, etc. So that is another. The second one is that init matrix, which was earlier using the init vec primitive, that was forbidding this collapse too because that for j was inside init vec. So what I have done is taken out that code inside the init matrix itself, and therefore although there is repetition of code now, but at least I am able to use the collapse 2 clause, right? So you have to do a trade-off between, let's say, code duplication versus parallelism in this case. Okay? Yeah, and here also I was playing around with num workers, and you can play around with num gangs and so on. Okay, so this is essentially it, which also signifies that the amount of work that we need to do once we have the sequential code towards the parallelism is not that high. Okay, so any questions on this one before I move ahead? Okay, so I'll close this and go to the next one. The second aspect, or rather the next step of LU is the LU decomposition, which also is part of some numerical methods where we solve system of equations, right? Where there is substitutions happening. So given a matrix A and a vector B, I want to find X such that AX equal to B, right? So that is our usual finding the system of linear equations, where A is, I mean, essentially A naught plus, I mean, A naught X naught plus A1 X1 plus A2 X2 plus A3 X3, like that. That is the first equation, all the way equal to B naught, and then B1, B2, B3, like that. There are n such equations which you can solve using this substitution. One of the methods uses converting this A matrix into the LU form, and then find out the values of y and x such that Ly becomes equal to b and ux equal to y. Right? So that is what you will get by substituting, so that then finally you will get the value of y, which you substitute to get the value of x. Right? So that is part of the LU decomposition. Again, you can solve it in a repeated manner, in an iterative manner, or you can solve it fully. So when we solve it in a repeated way, you get some sort of an approximation, and that is what I am showing here. X of I and y of I are two vectors, x and y. How do you get the values is given by this formula. Again, I don't know how to obtain this formula. Hopefully, there will be some method using which you can get this formula in place. But our job as OpenACC developers is to, can we implement this formula in our program, and then can we parallelize it? Right, so I'm going to open the LU decompose.c, and that will, maybe I'll open the final parallelized code itself, and that will give us the idea. Okay, so again, the main continues to remain very similar, where we have A, B, X, and Y. These are the 4 arrays that we require. And then data clause is going to help us create all these. And finally, it's only X and Y which I need to get back, right, from the GPU. In fact, you can possibly get only X, and that might turn out to be sufficient. Right? So depending upon what you exactly want to right? So you might get only X. So I initialize the matrix using a similar form as before, initialize the vector B using some random values. And then I perform an LU decomposition, LU method, which was what we had earlier. That is our LU part. And then I have the decompose part. Right? So the decompose method is the one that was using these equations. So that implementation uses, again, 2 for loops, one here and another here. And I can parallelize these separately using the loop clause. And then I also make use of the present clause, because the data clause has already created these arrays on the GPU. Right? So what does this particular code do? Well, in general, we don't have nested parallelism supported in the current version of OpenACC. So, but in case it gets supported in future, you might be able to make use of that ACC loop. So loop essentially means that it is auto. So you, no, sorry, it is ACC loop. Yeah, I don't think it is causing any problem or causing any additional benefit. Yeah, so I think even if you remove, I think that is not going to cause any problem, right? So, however, the issue here was that the if I talk about a single loop I, then there are multiple statements inside this particular loop, and that forbids me from using a collapse. And the same thing happens here. Thankfully, as far as the first loop is concerned, that can be converted. For example, this W, I can directly use B of I and get rid of this statement here. And then actually no, right? So you will have Y of I here. Yeah, so I can possibly use Y of I here. Yeah, maybe I can use Y of I directly here, and that will take care of this. But then how do I do B of I? Maybe I have to copy B into Y first, and then I can get rid of this type W equal to B of I also. Right. So once I do that, I get rid of this statement as well as this statement. Then the loop becomes a standard one or normalized one, and then I can use a collapse clause. That unfortunately will not be possible directly in this context because there is a similar statement which is coming into picture here as we had in the context of LU where we had this division. Right? In a similar manner, there is a division involved here. So one possibility is, of course, that you can convert this inner loop also, split it into this part. So there is one loop nest corresponding to the first part, and then another loop nest which contains for j, for k, and only this state. No for k. There is for j, and then there is this statement inside for I. So that is another way in which that can be done. In which case, for the first part, you will be able to apply the loop nest or collapse or tie. So that can be done, but whether that will be beneficial or not, I think that profiling might be able to give us that information. All right, so any questions on this part so far for the LU decomposition example? Okay, so I'm going to move ahead from here. So this was primarily what I wanted to cover, but there were two other questions that came up yesterday's discussion, which I tried yesterday and I thought might be helpful to some of you. So that I would like to cover in the remaining time. So first one was multi-GPU processing. So is it, we know that multi-GPUs are supported in OpenACC. I just didn't know how to do it. But so yesterday I looked it up a little bit, and at least I have one small simple program running, which shows that different parts of the code are running on different GPUs, right? Possibly at the same time. So how does the code look like? We have certain APIs in OpenACC.h, and ACC get num devices gives you the number of devices available, but for that we have to specify what type of devices you have. So that type is specified as a parameter. You can have ACC device NVIDIA, and there might be ACC device AMD, and so on. So in this case, since I'm dealing with NVIDIA GPUs, I get that number and I try to print it. I got that number output as 2 correctly because the machine on which I was running, it has 2 Volta GPUs. Then there is a pragma called ACC set device underscore num, and then I specify the number which starts from 0, 1, 2 like that. So I can specify that, and the rest of the code remains the same. So the parallelism, that doesn't require us to use a particular device in that. You can just use it once, and then the rest of the code, even if there are multiple pragmas here, it will continue to happen on device number 0. And then at some point you can start using device number 1, and the rest of the code, rest of the pragmas will refer to that particular device, and so on. And you can actually do it inside a loop, so that part of the code runs on GPU 0, another on GPU 1, and so on. Okay. How do I know that it's actually running on multiple GPUs? Well, the profiler output can give you this information, which so far we have ignored because it was all device num equal to 0 in all the cases. So that actually tells you that it is different kernels are running on different parts. Right? So that way you have it
running together or separately on different devices.
So whether this is running together or in separate devices, in this case it is running not together, it is running one after the other. But
so maybe after this num gangs and async will help, is it?
Yes, so if I add async, hopefully this will give. I didn't try that, but hopefully that will work. All right. Any other concerns, questions on this particular code? All right. So that was one part. The second one, which Durbajyoti had asked yesterday, is about the, let's say, is there any library which you can use like kublas, which is used for the BLAS operations. So it turned out that I mean kublas is there for CUDA, and it turned out that you can actually have combination of CUDA and OpenACC in the same binary. Right? So how that gets done is you can write your simple OpenACC program. So again, this is one small example where we have an OpenACC function which has a certain pragma. And then there is another code which is using kubla. So this one is actually a link which you can refer to. So there is a kubla's example given on the NVIDIA site. What I did inside these kubla's functions or the main function there, I just called OpenACC just to check the interoperability. Right? There is no correlation between the kubla's call and this OpenACC call, which can possibly be done. But currently, I just wanted to check how to make sure that these are working together. So it's not very difficult, but it's not trivial either. So what we need to do is to have these two codes separately written. Let's say this is openacc.c and this is CUDA.c. And I then need to compile these separately using different compilers. Right? So this OpenACC code I will compile using PGCC, and the CUDA code, which uses kublas, I compile using NVCC. Right? So in a similar manner, but I compile it only to an object code by specifying -c parameter. These two object codes, then I can combine again using PGCC. So that OpenACC.o and CUDA.o, these need to be combined into final a.out. And I might have to specify L kublas because I'm using that. And then CUDA runtime library might also have to be added to make sure that this code compiles to a.out. And then I saw that it is giving the appropriate answer. So that CUDA code actually runs the kublas calls. And after that, it calls the OpenACC pragma and then prints this and so on. So all of this happens properly as expected. So this is again one small basic check to see that CUDA and OpenACC can be combined. But yeah, you will have to learn more if you are making use of this. Any questions on this particular part?
So actually, what I was looking for is something which was written purely in
OpenACC.
Yeah, for example, we did this LU decomp to solvent equation, right?
Right.
So our BLAS libraries, the ones we use right now, have those equations ready. I mean, those methods ready.
Correct.
So there is no library which is written purely OpenACC. We can just call, plug and play, and have answers, right?
That's I couldn't find any which is probably well known.
Yeah. So yesterday, I think someone shared a link that is some support is there, but it is not a total like LAPACK library.
Exactly. So these are not mature frameworks to the extent I know. But then OpenACC itself is developing, so maybe we should not expect too much from these libraries. But yeah, maybe at least to get the initial part done, we can use some of these libraries for at least some of the basic functions. The others we will have to implement on our own.
Yeah. Okay.
Right. All right, so we come to the end of the this kind of course, except for the exam, and we covered lots of different aspects in these 10 days. We looked at the introduction to the basic aspects of GPU, then we looked at OpenACC Hello World and some compilation issues, etc. that come up. We then looked at compute constructs, parallel kernels, and loop, which were allowing us to perform the parallelization easily. and distribute work across different threads. Then optimization of the data transfer we did using the data construct. We then applied it to certain vector operations, and by doing different things, we learned a few other aspects related to the compilation as well as optimizations. We applied those then to the matrix operations yesterday and learned a few more things about that. Today we looked at the substitution cipher as one application, but then we also looked at the LU part and the LU decomposition part as other examples. Towards the end, we also looked at the simple program to do multi-GPU processing, as well as how to combine OpenACC and CUDA. So that is what I have for this course, except for tomorrow's exam, which will be on these topics. Hopefully, if you have done your exercises or you have made your hands dirty, you will be able to solve most of the problems. And let's see, so we'll meet tomorrow, and you might not even require 1 hour for solving the questions. You might be able to actually solve it much faster, in which case we'll see. We might do a photo session maybe a little earlier. And I'll also request you for your feedback tomorrow after the exam. Of course, you can write to me later also, but if you want to discuss it during the meeting, that is also a good thing. All right, so I will stop here from my side. If there are any questions, we can take those up now. Nitin has one question. What additional resources would you recommend in terms of URLs, books for further learning? I have some resources. I'll share that with all of you. Sure, I'll do that. So some of these resources are actually useful. Okay, so whenever you are looking at resources, the first thing I would suggest is look at the year in which these resources are made. If these are recent ones, those should be better, preferred, because some of the older ones may not be looking at all the constructs that get supported and all the facilities which get supported in the latest OpenACC version. But yeah, I'll share some resources. Hopefully that will be helpful. Sure. Dhurajyoti says, okay, thank you. Have a program speed up competition as the test. Sure. I think one of the important feedbacks was about this GCC part, because I see that not all of you are able to run these codes really. Some of you are able to, but not all of you. And I really wanted students to spend some time with that. But if Colab is, I mean, we don't know how to run it on Colab, then that is not going to be working. I also looked up some of the GCC documentation and realized that all these constraints exist. Although it supports OpenACC 2.6, I think, but there are the constraints that, for example, you cannot have the same variable in two different clauses. For example, we were facing that create clause and copy out clause of C. It was not, it was giving some error, right? So those constraints exist. In the context of GCC's support for OpenACC, but by and large, I think there are enough constructs which are supported in OMP, in the GCC world. So I would like to probably spend some time there so that at least students are able to run it on Colab, and then subject to that, some other constructs which are there in PGCC, I can always teach explicitly later. Yeah, and once students are able to do that, then I think the competition will definitely be a very good thing. Where I start with a sequential code, give all of you the sequential code, and whoever gives the most speed up, I think that will be the winner. And we can actually have teams and so on. Just also need to take care of correctness checks. Yes, sure, we should do that. Sure. Okay, any questions, any concerns? All right, so we'll stop here, and we'll meet tomorrow again at 6 o'clock. Request all of you to be there. I think it's just for self-assessment, some tests, so that we understand whether we have learned the basics properly and we are able to analyze the codes and so on. Right. So see you tomorrow at 6 o'clock at the same link. Bye.